An atomic nucleus is surrounded by a strong, repulsive electrical field. This defensive field can only be penetrated by particles traveling at very high speeds. To study nuclear transmutations, we need a plentiful supply of these high-speed particles at energies which can be varied. When accelerated electrons strike a solid, X-rays are produced. The faster the electron, the harder the X-ray. The first nuclear transmutations with laboratory-accelerated particles were produced by Sir John Cockcroft and Professor E.T.S. Walton. This is a model of their apparatus. Charged hydrogen nuclei were accelerated with a high voltage, produced by the use of transformers, condensers, and rectifying valves. High voltages needed for the acceleration of particles have also been produced by electrostatic machines of the Van de Graaff type, which are similar in principle to the Wimshurst machine. But to study interactions between fundamental particles, we need still higher particle energies. So it's been necessary to produce more and more powerful equipment. Such machines do not rely on the production of high voltages directly. A high ultimate energy is achieved either by moderate voltages applied to the particle a large number of times, or by accelerating the particles in a moving field. This latter type of equipment is known as the traveling wave linear accelerator. This machine provides a silent, compact, high-intensity source of X-rays for therapy and nuclear research. Now let's see how it works. An electron gun produces streams of electrons. The electrons could not travel through air without colliding with other particles. But if the gun is inserted into one end of a long cylindrical tube, which is then exhausted of air, the electrons will continue on their paths towards the other end of the tube. This end carries the target, which we want the electrons to hit. But most of them would miss the target. We want all of them to hit it. By surrounding the tube with a focusing coil, the electrons are directed along one central path. Now they all hit the target. In the linear accelerator, the electrons hit the target at a speed approaching the speed of light. The velocity of light is 186,000 miles per second. The symbol small c is used to express this. The velocity of the electrons produced by the electron gun depends on the voltage at which the gun is operated. For instance, a potential of 50,000 volts would produce electrons traveling at 40% C. $15 million volts would be needed to achieve 99.95% C. But for electromechanical reasons, this is impracticable. 40% C is easily achieved and doesn't involve serious insulation problems. Electrons at this velocity can be further accelerated by the use of energy from another source. A magnetron can produce a high-power electromagnetic wave without the use of extremely high voltages. The wave is fed into a rectangular waveguide where it adopts this form. It's conducted to the doorknob transformer, positioned in front of the electron gun. The transformer passes it on into the cylindrical tube, which also behaves as a waveguide, where it now adopts this form. The field due to this wave is alternately positive and negative. The electromagnetic field strengths and directions of operation of the wave are like this. The electron is a negatively charged particle. If two electrons are brought together, mutual forces will thrust them apart. Also, if two positively charged particles are brought together, mutual forces will thrust them apart. But if a positively charged and a negatively charged particle are brought together, they'll be mutually attracted. If a positive field is substituted for the positive particle, the electron will be drawn through the field. Now, suppose that the field were moving along the cylindrical waveguide at the same speed as the electron arriving from the gun. At first, the electron would accelerate while being drawn through the accelerating positive field. It would then come under the retarding influence of the negative field immediately ahead. But if the HF wave were made to accelerate with the electron would not come under the retarding influence of a negative field. While it's in this position, the electron will be gaining maximum energy and constantly accelerating. So to keep it in this position, the wave must also accelerate at the same rate. Control of wave velocity is achieved by loading the cylindrical waveguide with iris plates. These are spaced at equal intervals along the tube, their apertures increasing towards the target end. The wave in the rectangular waveguide is traveling at a phase velocity of 140% c. On entering the cylindrical waveguide, corrugated by the iris plates, each field of the wave is slowed down to 40% c, which is the injection velocity of the electron. Then the changing guide dimensions in the iris plates permit the fields to accelerate. By the time they reach the target end, the phase velocity is 99.95% c. The surplus HF energy is returned to the system by other guides. Now, if electrons were injected into the positive field under these conditions, they would gain energy progressively. But electrons do not emerge from the gun at favorable intervals to position themselves correctly. They come out in a continuous stream. Those which are injected into a retarding field will be rejected and lost. Those which are injected into an accelerating field will bunch together and continue to gain energy from the HF wave. So, finally, groups of electrons will strike the target at a speed of 99.95% c, and hard X-rays will radiate from it. The surplus HF energy is fed back from the target end through a subsidiary waveguide to a device known as the rat race, and recirculated with the power from the magnetron. During its journey down the tube, each particle increases its mass 30 times. Here is a drawing of a 4 megavolt linear accelerator for radiation therapy installed in the hospital at Newcastle. The magnetron and rectangular waveguides can be seen here. In this case, the machine is mounted on a gantry, which allows the X-ray head to move around the treatment table, which can be raised, lowered, rotated, and moved horizontally. In the adjoining main control room, this pump, in series with an oil diffusion pump mounted on the gantry, maintains a vacuum in the waveguide system of 1/300 millionth of an atmosphere. The X-ray technician brings the machine into correct running form on this main control panel. Here he controls the voltages, the modulator waveforms, and the focusing of the electron beam in the accelerator. In the treatment room, the patient is set up accurately in position. The gantry travels in an arc so that the beam of radiation will always pass through the same point in space. A flexible pointer on the X-ray head ensures that the patient is placed at the correct distance and indicates the point on the skin at which the beam must enter to reach the part of the body receiving treatment. Another pointer shows where the beam will emerge. Both pointers are removed before treatment begins, and everyone but the patient must leave the treatment room to avoid danger from sustained exposure to radiation. The radiographer at her control panel sets the prescribed dose of radiation on a dial and switches on the X-rays. She then observes the patient through a periscope during treatment. radiation from this 4 megavolt machine penetrates much further than that of ordinary deep therapy at 250 kilovolts, and treatment time is shorter. As the maximum doses recede 1 centimeter below the skin reactions are practically nil. The machine counts the dose in units of 10 roentgens and switches off automatically when the preset dose has been given. Apart from its clinical use, the linear accelerator is an important advance in the development of research in nuclear physics.